In this video, I'm going to run through the complete analysis of a simple linear regression model for an example that is going to relate two different body measurements. So, if we just run through the steps in a simple linear regression analysis, the first step is to formulate the model. So in this case, I'm going to look at my data. So let's see, here's my data set. And here's my data. And I've got arm measurements, which are the upper arm length measured in centimeters. And this is a data set of 75 individuals. And then I've got height, which is the standing height, also in centimeters for those same 75 individuals. And I'm going to try and model a linear relationship between these two variables. And I'm going to set the predictor to be arm, the upper arm length, and the response variable to be height, the standing height. And I'm going to see if there's a linear relationship here and see if it makes sense for me to be able to predict the height of someone based on their upper arm length. So that's going to be my model here. I'm going to have a simple linear regression model that relates these two variables. Next, I'm going to look at the data in a scatter plot. So before I fit any models, I'm going to just take a quick look just to see what my data looks like and to see if it might be reasonable to fit a simple linear regression model in this case, because you can often tell when you look at the data in a scatter plot whether what you're trying to do is reasonable or not. And in this case, I would say I've got a good chance of getting a good model here because I've got what looks to be a fairly linear relationship between the two variables in my scatter plot. Next, I'm going to estimate my model using least squares. So I can do that using this function here. And then I'll summarize the fit of the model. And then I'm going to evaluate the model using the three methods that we talked about earlier. So the regression standard error S is this number here. And the way that we talked about interpreting that number was to multiply it by 2. So that would give me 12.5. And I can say that if I was to use this model to predict height from arm, I can expect to be accurate to within approximately plus or minus 12 centimeters at a 95% confidence level. Next, I'm going to look at the coefficient of determination. So that's this number here. And I'm going to express this as a percentage, so 65.8% of the variation in height about its mean can be accounted for by this linear association between height and arm. And then finally I'm going to look at the population slope, B1. So here's my estimated slope. Here's its standard error. And if I divide the estimate by the standard error, I get this t statistic here. And that has a p-value that's essentially 0, smaller than 2 times 10 to the minus 16. And so at a 5% significance level, I would reject the null hypothesis in favor of the alternative that the population slope is not 0, and conclude that there is a linear association between these two variables. If I was to do a one-tail test here, do an upper tail test, the p-value for that would be half of this two-tail p-value. So again, a number that's essentially 0, and I would conclude that there's strong evidence of a positive linear association between these two variables. The other thing I could do here is I could look at a confidence interval for the slope, and that's given by these two numbers here. So I can say that I'm 95% confident that the population slope B1 is between 2.53 and 3.55. checking the model assumptions. So I can do that with a residual plot. So remember, as I scan the plot from left to right, I'm thinking of what is the average residual? Is that staying close to 0? And I would say it is. I'm thinking about the variance. Is the variance staying roughly constant as I move across the plot? And I would say it is. Are there any strange patterns that might indicate lack of independence? No, I don't think so. And then I can look at either a histogram or a QQ plot to determine whether normality is reasonable. And given that the points are roughly along the line, I would say normality is reasonable. So all the 4 model assumptions check out. So I can go ahead and interpret the model. And so we can look at a graph again, and this time we can add the regression line. So that summarizes the relationship between height and arm. If I look at my estimated intercept of 53.8, that would give me the expected or average height for someone who's got an upper arm length of 0. Well, that clearly makes no practical sense. So I can't really interpret 53.84, but I can interpret this number, and I can say that as arm length increases by 1 centimeter, on average height tends to increase by 3.04 centimeters. And if I was to put an interval around that, I could say that the increase in height for an increase in arm length of 1 centimeter, we're 95% confident that that increase in height would be between 2.53 centimeters and 3.55 centimeters. And then finally, I can think about estimating the mean of y and predicting an individual value of y for a specific value of x. So for example, let's think about someone with, or let's first think about a group of individuals with an upper arm length of 38 centimeters. What would their average height be? So that's going to be a confidence interval for the mean, and we're 95% confident that the mean height for those individuals with arm lengths of 38 centimeters would be between 168 centimeters and 170.9 centimeters. Alternatively, we could again look at an arm length of 38 centimeters, but just focus on one individual and try and predict that individual's height, and that's a more difficult problem. And so our interval has to be wider to reflect that added difficulty, or that increased uncertainty, let's put it like that. And so now we're 95% confident that that individual would have a height between 156.9 and 182 centimeters. So those are the steps in a simple linear regression analysis, and I've just run through an example that relates height and arm length for a group of individuals. And that brings us to the end of this chapter. In the next series of videos, we'll extend what we've looked at for simple linear regression to multiple linear regression, where we don't just have a single predictor x, we have multiple x predictors.